Thank you. So the title of the talk is Challenges in the Deep Learning-Based Side Channel Analysis. This is a topic I'm working quite intensely for the last couple of years. So let's say it makes sense to give some overview of the things we did, the things we plan to do, and the things that we kind of consider to be interesting. Everything I will be talking about today is actually done in collaboration with many of my colleagues. So here I will mention only a couple of names: Guilherme Perin, Li Chao Wu, Shivam Basin, Leila Batina, Dirman Tuyap, and so on. So from the outline, you can actually see I have a lot of topics to cover in 30 minutes. That there will be very short exposition per topic, but then we will have also time in breakout room if you are interested in any details. So very short introduction for who maybe doesn't know about side channel attacks, about profiled side channel attacks. So implementation attacks are those attacks that do not aim at the weakness of the algorithm, but at the weakness of the implementation. And common examples, types of implementation attacks are side channel attacks and fault injection attacks. And then within side channel attacks, we commonly divide it into two categories. We divide the attacks into direct attacks, like simple power analysis, differential power analysis, and into profiled attacks. Profiled attacks are also commonly known as two-stage attacks. And today, profiled attacks are considered actually to be the most powerful type of side channel attacks. And why is that? Well, because we assume a different threat model, we assume attacker to be more powerful. What does it mean? Instead, like in direct attacks where there is one device that we want to attack, in profiled attacks, there is basically two devices. There is the device under your control, and there is the target. And the attacker uses the device under the control to learn as much as possible about the target, and then uses that knowledge to really mount the attack. Of course, because there are two stages, such attacks are more complicated than the direct attacks. But on a plus side, if you build a good model, then you have a chance for your attack to be extremely successful. So when you are really attacking the device under attack, hopefully you will need only a small number of measurements to really break the target. And actually, a common example of profiled attacks is template attack. And this is the most powerful attack from the information theoretic point of view, of course. But of course, for that attack to be really so powerful, you kind of need unrealistic assumptions. And then let's say last 10 years, a little bit more, people started using machine learning for profiling attacks. And they actually recognized, okay, the same setup we discussed, and this is the setup I show here, actually maps quite nicely to one machine learning paradigm. And this is the supervised machine learning. So let's see how it would work in supervised machine learning. First phase of supervised machine learning will be the learning phase. Here we have our PC, we have our copy of a device. Based on that copy, we learn our model, our machine learning model. And then once we want to attack, or let's say more in the machine learning terminology, test, we use that model and we use the measurements from the device that is under attack to infer what will be the possible key. And this is very natural. So profiling attacks is very nicely connected with the supervised machine learning. And when we talk about machine learning process in general, in essence, we can have, let's say, these 5 phases from beginning to the end. First phase would be something like raw data, so data collection, which is, let's say, I'm skipping that. This is how you would really engineer. What do you want to do? How would you obtain the measurements, so data acquisition, and so on and so on. The second phase is data preprocessing. This phase would commonly consider techniques like removing duplicate measurements, removing measurements that are not complete, and similar. Although we will see very soon, we can do very cool things in data preprocessing phase additionally in the setting of side channel. One of those things would be, for instance, data alignment. If you are attacking a target that has countermeasures, maybe some desynchronization, you actually want to align those traces. And this is what you would do in the data preprocessing phase. The next phase would be feature engineering. And this was a phase of extreme importance for template attack and for simpler, let's say, classical machine learning. There, it was very important that you select a relatively small number of features that are actually representing the leakage the best, and then using those features, breaking the target. Next step, model selection, hyperparameter optimization. Well, at the time when we had only template attack, model selection was very simple. We did template attack. Template attack has no hyperparameters, so even simpler. And then once we went into machine learning, there are more techniques there, more complicated techniques commonly have also more hyperparameters to tune. There's something, just general info. So we had more and more work. And finally, last phase would be the model validation or testing. So the phase where we actually try to use our model to, let's say, in side channel context to break a target. Now, when we talk about deep learning, this graph kind of changed. Feature engineering became less important. It's still important because many of side channel measurements are extremely long, so have many, many features. But differing from before, when we were selecting specific features like feature 75, then feature 200, then feature 500, and so on. With deep learning, we actually plan to take a window of features. So we try to recognize what is the most important part, and then we take either the window of features, or if our deep learning algorithm and setup is powerful enough, we even take raw features and then leave everything for the algorithm to resolve. So this is one of the big advantages of deep learning. Feature engineering is, let's say, almost non-existing or very simple. On the other hand, this model selection with deep learning is not very difficult because currently we use only a couple of different techniques, but there is a lot of hyperparameters to optimize. So suddenly this phase became more complicated. But because of also bigger power of algorithms, deep learning algorithms that we have, our model validation is with deep learning more successful. Indeed, when we talk about more difficult targets, something that is protected with countermeasures, with classical machine learning, with template attack, many of those attacks are not very successful, or they need extremely large number of attack traces to break the target. With deep learning, there is quite a lot of settings, at least in publicly available setup, so data sets that are publicly available, where we are really approaching that ultimate dream where we can break the target with only a single measurement in the attack phase. So when we want to talk about, let's say, state of the art, or what is happening, what are the success stories for deep learning and side channel attacks, I will mention here a couple of works that we recently or relatively recently did. The first one is when we try to use deep learning in the pre-processing phase. So the phase, like I said, that was commonly not done a lot with machine learning, but actually there can be something that we can do. And what is it? So if we talk about more realistic data sets, they will be protected with countermeasures. And because of those countermeasures, side channel attacks will be more difficult to succeed. But many of those countermeasures can actually be considered as noise. And since if we consider countermeasures as noise, we can ask the question, okay, is there something in the machine learning domain that can help us fight against noise? And actually there is something that is called denoising autoencoder, where the classical technique is used to reduce noise. And for us, We recognized several different types of countermeasures like Gaussian noise, random delay interrupts, desynchronization, jitter, shuffling, that we can actually take the dataset with noise, remove the noise or remove part of the noise and make the attack more powerful. How do we do it? Well, the denoising autoencoder consists of two parts, encoder, decoder, where you basically want to ask, on one side you put the measurements with noise, on the other side you put measurements without noise, and you ask your machine learning algorithm, find me a function to map from one to the other. If you have a function like that, then later you can use that function and say, well, now again I have noisy measurement, I use that function, and hopefully at the output I will get measurements with less noise or even without any noise. So here I will just show you one example, what happens, for instance, for desynchronization. This is a hiding countermeasure that is of global character. So you take your trace and you move it left or right, however you want to look at it, for some value. So it's a global because it moves everything for that value. Left figure shows what kind of result we can get, for instance, with the technique that is commonly used to reduce the effect of misalignment, and this is the static alignment. And we consider three different techniques: template attack and two deep learning techniques, multi-layer perceptron convolutional neural networks. So you can actually see that we can get quite good results if we denoise with static alignment, especially for CNN, but the other two techniques suffer quite a lot, and template attack cannot even break target with 10,000 attack traces. But if we would apply denoising autoencoder, so here CAE means convolutional autoencoder, we can actually see that all the techniques work nice, and especially multi-layer perceptron and template attack are much more successful than before. What's the moral of this story? We can use deep learning to increase the performance of the attack, but that attack does not even need to be deep learning attack. So first step, we do deep learning to denoise, and then we can even use much simpler techniques like template and break the target. Next, what I will again very shortly mention is a topic that is very important for side-channel deep learning, and this is the hyperparameter tuning. Basically, it is deciding how will your architecture look like and how will your training process look like. But this is quite difficult thing to do. The more complicated algorithm you have, commonly it will have more hyperparameters to tune. And of course, different algorithms will also have different hyperparameters to tune. And hyperparameters you tuned for one setup does not mean that it will be good for the other setup. So different data sets. So how people commonly do it? Well, commonly people do either random search, where they try to find randomly good hyperparameters, or some sort of grid search, or they use, let's say, more advanced techniques, or also what we saw, let's say, in last year, a little bit more happening inside channel community, we are trying to find a good methodology. So what is a methodology? It would be some more proper way of set of rules to follow to obtain a good deep learning architecture to break a target. Unfortunately, we have only a couple of methodologies, and they are not always easy to expand, but those methodologies that they are there work very nicely for the data sets that were designed to. And this is just a very brief slide to show you the general design, how it looks like most of our convolutional neural networks that we use in side-channel analysis. So this is something that is called VGG-like design. So what we did recently, let's say that goes more into that direction of advanced techniques for hyperparameter tuning, would be going into automatic hyperparameter tuning with reinforcement learning. So we built a setup based on reinforcement learning that has a proper reward function based on guessing entropy, accuracy, whatever you want, and tries to find good performing neural networks. So here I again show just one example. This is on the ASCA dataset, which is a dataset protected with masking, where we can see that we can find neural networks that are very small. So RS here means reward small. It means do not only aim to get a neural network that works well from the attack perspective, but that is also as small as possible. So we can see that a data set that was relatively recently proposed and was considered more realistic, ASCA, already becomes very easy to break. So we need less than 100 measurements or around that to break it. Next is a very interesting topic because it goes more into reality, and this is the portability. So what do we do when we do profiling attacks? Well, remember I said there are two devices, one you train, the second one you attack. But unfortunately, in reality, we commonly have one device, and then we artificially divide the measurements and say this is for training, this is for attacking. But the question is, how close is that to reality? Or to say differently, what happens if we really take two devices? So here I show only two small examples. This is one example where we train on the same key and same device. And here is the example where we actually train on one key or set of keys and one device and attack different device with different key. So you can see while some attacks are good, many attacks become extremely unsuccessful. And this is even a very simple target to break. So I'm not sure how I'm doing with time. So how long do I have? 10 minutes?
10 minutes, 5 to 10 minutes you have.
Okay, great. So I will need to be much faster. Next, what I will just briefly mention is the question when we have a neural network. How do we know that that neural network is not way too suboptimal? Or to say differently, how do we know that we really found architecture that works, that is as small as possible, so that it overfits as little as possible? And recently, we tried playing with a technique called pruning. This is also known as pacification, where we systematically remove parameters from neural networks. And here I just give some pseudocode for a very simple pruning technique. And here is a little bit more in a graphical depiction. So what do? You take neural network, you train it, you remove some weights that are not important. How do you know it's not important? Well, you see how big is the weight or how much the weight changed, and then you remove the smallest ones. And then you can, for instance, either retrain, so reinitialize with the existing weights, or start again with the new weights and see what kind of attack performance you get. Again, this is a result for ASCA dataset. What is important here to note, even if when we took a very small neural network, you can actually see that we managed to reduce 60–70% of that neural network size and obtain even a bit better results because of the overfitting or very similar results. Why is this important? Well, simple reason, because it tells us that while in side channel analysis and deep learning, we use relatively small neural networks compared to other domains, but even those small neural networks still seem to be way too large for what we need. Let's say somehow connected with pruning, there is also a technique called ablation. And this is more to help with explainability, to understand how a system, how a neural network performs if you remove certain part of a neural network. Think of it, you have a neural network and you randomly decide, I will remove this set of neurons. Then you again see how the neural network works. If the neural network works the same, you can easily conclude, okay, what I removed was actually not important. If the neural network changes the behavior, either worse or better, you can see, okay, those neurons were important. So we needed to design an ablation methodology that is applicable for side channel analysis. After some effort, we managed to do that. And what kind of result did we get? So this is not the easiest graph to interpret, but let me try to to do it very quickly. So here, ref before, ref after is what happens when you train a neural network for a certain goal, then add Gaussian noise and try to break whatever has the Gaussian noise. So for instance, we can see here, if we do that, we actually do not break the target, or we have guessing entropy equal to 4. If we retrain the neural network after we change the target, we can succeed perfectly. While here in columns, we can see what happens per layer if we remove neurons and then retrain. So whatever is below 0 means performs worse, whatever is above 0 means performs better, and before means before retraining, after means after retraining. So why is this important? Because it shows us that, for instance, when we work with Gaussian noise, neural networks like to process Gaussian noise in the beginning layers, so beginning process. Compared, for instance, with this figure, this is for desynchronization, where we actually see that neural networks like to process desynchronization in deeper layers. So this is just a very small set of experiments. We did actually much more experiments, and we saw that there is a way how neural networks process when they need to work with different countermeasures. Simple countermeasures that neural networks like to process in the beginning layers, while more complicated countermeasures go deeper and deeper. By using this technique, actually, we can kind of explain what is happening in a neural network. And if a neural network does not work well, we can understand what do we need to change in a neural network to actually make it work better. So this is, let's say, something more in the explainability perspective. Okay, since I'm for some reason relatively slow, I will now just mention that what I talked up to now is attacks on block ciphers, basically on AES. And this is, it seems, the main current of people, of the main body of work in side channel community. Deep learning considers block ciphers, considers AES. The question is, what kind of results can we get for public key crypto? And we recently played a bit with protected elliptic curve implementations. As protected microsalt implementation. And we designed what we called deep learning-based iterative framework. What is it? So when you are in the unsupervised setting for public key crypto, you do something like horizontal attack. But that horizontal attack will often be marginally better than random guessing. You are guessing the bits, so value 0, 1. So marginally better means you will have somewhere around 52, 54% accuracy. But that's very far from getting the exponent value. So we designed a framework where you take a set of measurements, you divide, predict, relabel, and in every phase of the framework, you actually remove part of the noise happening from the horizontal phase. And what kind of results we can get? Actually, we see that we can get from accuracy of 52% or 52.3%, the smallest we tried, up to 100% accuracy. So we can actually correct wrong bits from the horizontal attack and have completely rebuilt the exponent value. So completely broken target. Okay, basically this is let's say on very short overview of, let's say, state of the art, what is happening. I will only mention we recently developed a framework called ICHSA for deep learning side channel analysis that has, let's hope, quite a lot of functionalities that can help people. So one functionality I will just mention is one-click script generation. Once you make architecture, make a tag, you can just do one click and you get automatically generated script that made that attack. So it makes your results very easy to reproduce, very easy to share. The framework is available on this link. It's publicly available. So if you are interested in deep learning side channel analysis, I recommend checking. Okay, so let's say this is a very short overview of what is the state of the art. But what are the challenges? What kind of challenges do we currently have? Well, while I said we have many ways how to select hyperparameters, I still think one of the big challenges is how do we do hyperparameter tuning, because we don't know enough. This is also connected with the second topic, lack of difficult data sets. Before, when I was giving similar talks, I was always saying lack of data sets. Luckily, now we have a bit more data sets, but since our state of art progressed, they are not any more difficult. So what we need is difficult data sets. Without that, it's very difficult. If we don't know what we are doing, is it really good attack, or is it that we are breaking something simply because everything works? Interpretability, explainability, common topics that are difficult for whole deep learning domains, so also for us. How do we do maybe possible countermeasures for neural network-based side channel attacks, and so on, so on. What are the directions that we can see, let's say, happening in last year or so? First is customizations. So many people start to think more and more, can we make custom architectures or parts of architectures for side channels? So for instance, custom layers, custom loss functions, and so on. Methodologies, new metrics. What is also a very cool direction recently done is leakage assessment. We actually saw that we do not need to use deep learning only to do attacks. We can also use deep learning to do leakage assessment. Something for many years, basically, we had only TVLA. And also unsupervised learning, which I believe it's a huge direction, maybe the biggest challenge, how to move to deep learning attacks that work in the unsupervised way. To conclude, currently, side channel with deep learning is in a very good shape. So what we know how to do seems to be very nice. We managed to break many different targets. What we use from deep learning perspective, it is much simpler than the things that other communities use in deep learning. The biggest general issue that I see what is happening is that while we manage to improve the quality of our attacks all the time, we actually do not manage, or we do not try enough to improve the quality of countermeasures against deep learning based attacks. Because if we break something with deep learning, fine, we know we broke it, but we actually do not get much knowledge how to make a safer design. So this is one of, let's say, big questions that we need to ask, how to also make better designs, not only better attacks. With this, I finish, and if you have any questions, I'm happy to answer.